post always these online. Okay. Last night I did some stuff with this the dates curve. So we found a function which is this fixed graph. So what it does, so sort of we pass with an axis. What it does is that it goes and then gets, in order to label in that axis, so it gets the actual case. So what it does. It's a very simple one. Then whenever so we require this again, I just pass this fixed graph from that figure, then we get the axis, we look at the first one, and then we go. That's what it is. This is undone. So, but what we didn't actually do yesterday was to select the order of autoregression using an information criteria. We do that now. That's very short. So if you remember, so in the very beginning of this code, then we have model which is, or sort of a function which is called AR select order, and that is autoregression to AR with exogenous variables X, model order selection. Right? So here, then there are inputs, that's the dependent variable, then you have the maximum DAX, which is sort of some number, so value, anything order something. Then we have the information criteria, which can be Akaike, can be Bayesian, BIC, or can be the Hanon-Quick. So all of the three that we actually know, so they are here. There is an option which is called Globe. Alright? I will tell you about Globe in a minute. And then some others. Alright, so let's maybe start with using this in a very, very simple setup. Alright. So here I will say, let's select a model, let's call it cell 1. So select the model number 1. And then we do AR select order. Now we pass the endogenous variable, which is the dependent variable. Let's have the max lag to be, say, 15. Correct. So you can actually pass seasonal to make it true. And then you add the period, which we decided that it is good. Of course, you can have it differently. Right? But I mean, sort of, you could do the following. You can have this, you can put this in a loop, and then look at some different periods, 2, 6, 4, and so on and so forth, and see which is better. Which is better in terms of, say, the best IC information criteria that you get, or you calculate the mean square error of the forecast out of sample, and then check which model is good. So with 2 periods, 10 periods, and so on and so forth. You can also have the seasonal true or false. So if you write a loop, then you can play around with those. And then it works, but that's sort of very simple. So you fix the period to 12, seasonal true, max like 15, and that's the dependent variable which is the eyes. So let's have a execution. So if I do that, then well, that's pretty fast. And then I get the selected model. Let's see what does it do. I mean, what does it actually choose? Let's maybe print cell 1 dot, so it has a lot of stuff. Maybe let's look at the variable, which is called cell 1. That's an autoregression order selection results, and then there are, let's go IC, so there are the periods which we set it true, right? So we have a trend, which is a constant, so there is just a mean, no linear trend, and so on and so forth. And there are the AR lags that we have, and it shows 13. Alright. So the number of lags that we have. Sort of using, so that's what we have. So AIC chooses 16. Right? And what does it mean? Well, that's the size, and these are the lags. Right? So these are the lags which are village. You can go look at them. Right? And then ARC 1, 2, 3, and 6, 7, 8, 9, 10, 11, 12, 13. So this stays at 13. Well, so it would be AR, number of lags that we have. And we can go now estimate this, as simple as that. So, well, I mean, the first thing is that we estimate this model. So you don't need to generate the model on your own, but this AR select actually generates the model. So we don't need to do auto-rec another time, rather we can simply go on. Right? For example, let's say I put it cell 1, fitted, alright, or estimated model, S, and that will be, right here we have cell 1, and in cell 1 there is a model. Alright, but that model simply gives us the model. Then we make it larger. Alright, so that's the model. And so here we can simply go on with fitting. So let's say we fit it. Let's fix the full type. And to page C0. And now we will have the model. Alright, so let's print cell 1 underline S. That's summary. Just to see what is it that this model actually estimates. So the coefficients, the modulus of the moduli will go to the roots of the polynomial, and so on and so forth. Okay. Hello, Dean. So we're good. Alright. Let's look at the results. Alright. So here we have the period. Alright, so this is what we have. And then these are the AR coefficients. Consider up to like 13 seems to be not relevant. And so on and so forth. So what we can do now, I mean, next is just to go do predictions and look at the diagnostics of the model as we have done with the previous. So you two that came, so we just repeat this few minutes. So this is where we stopped last week.
Yesterday.
Last session, sorry, that's automatic, because this is a week supposed to be a weekly. So we just teach 1 week and then go on. But in this sort of time period, then I give the students a lot of exercise, but we don't have so many exercises. Anyway. So you're with me. Okay. So that's the 5. So we have the select model. So sort of I want to choose the order of the model using information criteria. Then we have the function. And then this function actually takes a number of inputs. One is says, okay, what is the variable that you want to repeat? Repeating for you. What is the variable that is the dependent variable? What is the maximum value? We want to do information criteria. And then there are some other options. There are many options, so I just played with some of them. So for example, one is that we want to have a seasonal effect. Alright, so which we set it to true. And this is the period as we discussed earlier. Alright. So but max like I set to 15. Alright. Maybe you type it. And then we can see, alright, so how many lags this model estimates? What are they? 1, 2, 3, and so on and so forth. And we saw that there are 13. Alright, so if I set it to 15, then it shows 13. This one is on. Oh, it didn't turn on. Alright. And then we do, I mean, we don't need to generate the model again. This guy actually has the model itself. Right? So that's an object which the model is in it. And then we do a fit. I was looking at a summary of the result. Oh, I thought you were going. Some are disappointed because I'm repeating for you and you want to go. when you run the model summary or the estimation, and then there are sort of well, inputs and results. So these modularly stuff are all bigger than one, so that's good. So the roots are out of the unit circle. Right? Now that we are here, we can start doing, well, let's look at the diagnostics. So that's the first thing I'm going to do. So I will copy paste this part of the code down there, and then look at the diagnostics. So this is cell 1 estimated. That's cell 1 estimated. That is the diagnostics. And this is to make the graph look smart. So these lines that we have is the number of lines which we use to calculate the, or sort of show the autocorrelogram of the residuals. Let's do that and take it. Okay. So that's the diagnostics as a figure, then we pass it to fixed graphs with the program which I told you, and then we get a small plot. So now let's look at that. Look at the residuals. They are better than previous. So it looks like that this one additional lab of 13 actually did a more or less better job compared to the previous. So here, if I look at this, then these big ones went away. Just they went down. There is still a little bit this series. That may be because when you look at the residuals, then there are still a little bit of random behavior. Specifically, so here around 90s, so it goes up. And that is where things were going up, and then when it comes to that's not so much, but it looks like there is a little bit of stuff there still in the residuals, but nevertheless seems to be at least captures the dynamics of it. The dynamics maybe because of the cycle, but I don't care, because I want to do forecasting. I want something that captures the dynamics. Specifically because here I have a lot of data, 600 or so data points. So if I look at this, and sort of, the deviations actually also became very small. Higher clockwise and lower clockwise. Right? So there is not much deviation. It means that in this model with 13, does a pretty good job more or less of capturing what is happening in the series of dynamics. Or linear dynamics. And then we are essentially with the forecast. Let's do the forecast. So for forecasting and then plotting, I will take this bit, and then that's with the forecasting part, and then we just let's estimate model. That's the name of it. This is what we have. So we do. This is how it looks. But I mean, there is not much of. Let's look at this is the series. That's what gets the peak, gets the cycle. So the confidence bands are fine. And they're not much better. Well, they're slightly better than the previous one. This is with 12. This is what you see is with 12. And this is with 13. Right? So the confidence band became a little smaller. Because the residuals we took care of a bit better compared to the previous residual. Right, so, and then these two big ones actually went away. So that's, okay. That was what we did. Now, let me actually do a little further stuff with this
select mode, or AR select.
Okay. One more. There is one more exercise to learn what is selecting of the lag work. And then we will be done. Actually, not done. I'm going to tell you a little bit further before that. Look, I mean, here we have the independent variable warranty, and then we have a constant clause summation j from 1 to 13, say Vj or Vj yt minus j plus some shock. Right? So that is what we have. It chooses lag 1, lag 2, lag 3, and so on and so forth. Right? That's sort of what we do. But maybe lag 5 is not relevant. Maybe. Well, why should I then? I mean, maybe 1, 2, 3, 4 are good. 5 not. Alright. And then 6 to 13 are relevant. Okay. Right. I'm saying this because I looked at the feedback, which is what I did yesterday. Let's look at the output. Alright, so that is here, well, I mean, these are the lags, right? So lag 1 is relevant, 2, 3, well, 5 doesn't seem to be, 6 is irrelevant, 7 is irrelevant. So sort of, in the beginning, those lags are interesting, then they're not, and then they are. Yeah? So maybe I can kick them out. Why should I actually estimate them all? So to speak, maybe I can reduce the dimension. Right? So that's the dimension, so the dimensionality can reduce. The dimension, or how many parameters we assume, we can make less. Right? So, and it what does AIC do? Right? So AIC wants this with, that is what we did. With 1 lag, with 2 lags, 3 up to 15. Right? So here, well, let's say the ARP. Alright? And then we have P equal 1, then we have C or PIC, or let's say IC. Then we have IC 2, then we have IC 2, up to IC 15, IC 14, IC. Then so that's sort of the lags, and these are the IC condition criteria, and then the one that is the smallest is this. So there is one. So it means that we have 13 modes to take care of. Right? But if I want some of those lags to go out, then the number of modes will become more. Right? So can you do the start with this? What I say, well, let's say this is the set of lags. Can we have 1? Can we have 1 and 2? Can we have 1 and 3? Taking 2 out. So look at, so you mean that here in this model, then I set phi2 to 0. So that will be also another one. So I'm not going from 1 to 2, but going from 1 to 3. I should go from 1 to 4, 1 to 5, 1 to 6, and so on and so forth. But we also start with taking 2 out. We start with 2. I don't actually use the first line, while only the second. There will be another model, right? Maybe that will be giving me a better answer. And then look at these combinations. I could also look at, say, 1, 2, 3. Or 1, 3, soft. 1, 4, 6. All of the 3. Starting with 1, maybe keep 1 out. All of the subsets of dimension 3 out of 1 to 13, which are how many?
Combination.
There are 13 dimensions without 1. And then I can go and then choose 4 out. But there are many. In calculate this, you see it's big. This is it from here. So on and so forth. We can actually look at all of the possible models we have. And very simple idea, alright? But the thing is that in all of the textbooks, when you look at them, then they actually, when they start talking about IC, and they say, all right, so put 1, now go to AR2, and then go to AR3. I mean, but one doesn't need to stay with that. ICs are designed for comparing modes, and they don't say which modes. So I can usually do whatever I want, whatever mode I can think. If I stay with the AR modes. So but that is computationally very hard. So because there are many modes, there are not 13, but there are how many? Can you tell me? So how many models do you have here in this frame?
All of this to the power of 13.
Yes, very nice. You should do calculation great. -1, right?
If we include just constant,
So well, that's the order is 2 to the power of 13. So 2 to the power of 13 models that you want to check. As such, it becomes very hard computation. What is attractive, but computation is not viable. Right? Then, actually, this is the place where data science can come in and help us. Right? Because data science comes from two sources. First, from statistics, that's the statistics. And then also on the data side. So we need some method that could help us to count efficiently. Look at all of these models efficiently. Right? This is something I'm not going to go deep because this is more financial econometrics and real data science course, right? But that's sort of because you asked me yesterday where this data science can help us. That is one situation. When you eat this AR select has an option which is called below. But you will see it takes a lot of time because that's not efficient. So let me take this. I will not be able to probably to run this in this class. Model selection using IC with global search. Alright. And that will be something like that. So just copy paste this. And then here I will call it cell 2. Here cell 2. That's another model selection method. Alright, so I don't know actually how much does it bring. Maybe it does. I don't know. Right? So I mean, that's the thing. You never know what how much this model can bring. Right? And then here we say, comma, there is something which is called below. By default it is off. Right? And if you turn it to true, then it will go count, so it will check all of the numbers. 1, 2, 3, 4, 5, so it will check all of them. And then calculate a model which is sort of relevant. Should we try? So let's try and then see if it finishes in 1 minute. And then we use it, otherwise we sort of but
I saw him say next time we have a number of fixed graphs, how do you report them? How do you
sorry, so that was something I said in the very beginning. Last night, last evening afternoon when I was bored, then I changed the code a little bit, made it a bit nicer, and that is what I did. Look, I mean the dates on this graph were looked at. And then I changed them by 45 degrees. The function is online. And actually this code that I have is already online. So you can download it. It's on the video page. And then you will see the function. So the function is actually very simple. What it does is that it gets this axis and looks at all of the labels and turns them by 45. I mean, if you don't have it, then you don't have it for now. Right? So your graphs will not be as beautiful as mine. but then that is what it is. But let's let it run. So we did long. Sorry, I mean, that will not be to the power of 13, but rather to the power of 15. Because the max stack that I have is actually, well, I mean, that was the model chosen. And then here we have a Pmax. And this Pmax, we chose it to finish. Oh, now I understand, because I mean, previously I was running this on the other laptop, but this is another one, I got it recently. And that's so fast. That's a 7-core, and each core is 2.8, so it's a very fast. So, well, now, let's look at the lags. Look, this is the lags. 1, 11, 12, 13. It doesn't choose 2 or 3 and so on and so forth. It doesn't choose them. With this good old way true. Alright? That was nice. Yeah, I mean, some of you that have Macs, maybe the ones that are fast, they will also be very fast with that. Anyhow, so that is the lags that we have. But, well, let's look at and then let's estimate the model. Let's look at the summary. Right. So that is the model. So these are the means. These are the lag coefficients. These are the modulus. So I mean that's an autoregression of order 13. So there will be 13 roots in any case. The model will be all bigger than one. All of the units are going to be and that is the block of the diagnostic. Well, that is this. Well, I mean, it sort of doesn't break much compared to the previous one, right? So, well, the funny or sort of nice thing is that these two are off here too. So these are the lags which are at the very end, 11, 12, 13, that are capable of capturing these lags. And that's not surprising, right? Because these two lags were showing up after 6 months or 12 months. 12 and 12. So a bit more than 12 would have been able to capture. Right, so that's sort of what we, I mean, as a side thing. And then, well, let's do the forecasting. Well, that's sort of a little better even. Yeah, so that is the model with 13 confidence bands. This is the model with, maybe not even. It's sort of more or less the same. Well, the confidence. But of course, I'm just looking at the confidence bands and so on and so forth. I didn't tell you anything about forecast evaluation. Alright, so that you sort of do the pseudo out of sample, one step ahead errors, calculate the mean forecast errors, and then compare. Right? And that's sort of, you can do it. It's, I think that's sort of, to get you involved with that, it doesn't make sense. But you have the forecast, you have the actual values, you can take a difference, take the power of 2 sum divided by the number, then we will be in forecast error. I think that is enough with class. So these are models which we have out of books. Right? Did you know them from Uwe Hasler's textbook? Of course, or sort of the course that you have had, right? But Uwe Hasler probably didn't tell you much about the sort of not possible in these 2 weeks to tell you everything, right? Probably he didn't tell you how to get a break or the trend. Did he? Do you know how to estimate a structural break? Probably not. Yeah? I would have been happy to tell you, but I have other stuff to cover. But I will give you a tool which does it for you. Without, well, the theory you know, it's not hard. Now we go to Python and then do something else with forecast. Something which includes sort of on estimating the trend. It understands the cycle, which is a long-term trend. Which for that, and if I want to teach you, then I have to tell you something on Fourier analysis. But I mean, that sort of doesn't work. So one needs a lot more time. So the package is used by Facebook, and was developed by Facebook. Sort of based on classical time series. So, but as I said, unfortunately, I can't tell you how what are the methods behind that package. There are essentially these type of the stuff that we have. But that captures a lot of the stuff, so the brakes, the trains, and so on and so forth, right? And also the cycle, so it all captures. So the package is open source. Well, it's the usual Python stuff. But there's also an R package if you're interested in that. And it is called Profit. Profit, you know the word. So that's the biggest key that you can. There's the most. So that's sort of a package which includes all of everything that the dynamics, seasonalities, takes care of the structural breaks, finds the trends, finds the cycles, and so on and so forth. So I will just tell you how to use it, okay, for this exercise. And then we'll sort of generate forecasts and then get the breaks and so on and so forth. That will be sort of interesting. There is also another package if you're already interested in the structural breaks and detecting that. I think this one Rogers. That's also a very stable, nice package. You estimate the structural breaks in the mean. Unfortunately, well, not unfortunately, but that's just takes the structural breaks in the mean. Profit, on the other hand, combines seasonal models. Or seasonal autorecord, or seasonal series, time series models. The classical R models looks at cycles and then gets the trends. And we don't need actually to do anything, we just need to pass the data in, and then we'll automatically understand what's going on. Automatically using models we developed in time series, they took them and then put them together in an efficient package. So that's very good. So let's, in this very same file, we go to Profit, which is the Facebook tool. Right? Facebook, you know. So you know what is Facebook. It's a company and then one uses to communicate with someone. That's a book for faces. Alright, let me tell you how this basically works. So what you need to do is, so let me go up there. Yeah, so here is the profit. So you need to import, you should install it. So click install Profit. That's the one. Well, I mean, there is very nice. So that's for the Python API, or uses Python, and so on and so forth. Right? So it's this installation. So you can either do that, or you have a PySR. Where does it show me R? Installation on R. Installation Python. So you pick install Profit with P small. That you need if you brought it to the ES. you're done, it's finished. Yes, very good. So let's use it. I'm actually I do some project now for sort of it's about optimization that sort of part of this forecasting where I use this. And I use other things too. And I show that this is not the best. There is good. It's good enough, but there are better models. And depending on the data. This actually model works when you have seasons. When you have seasonalities, then it's actually a very good one. A strong seasons of the data that you have. And well, these are like say demand for electricity. Most of the season. Right. So this one. And then some other seasonal stuff that the one has essentially. So let's go on. So here we import sort of from the so we don't do it all, actually that's very big. So from profit we import profit with capital P. Alright? That's sort of what we do. Now, I mean this one so here we have the data, and the data looks like let's look at the data. And the data looks like so. So it has a date and has a variable which is called eyes. So this profit actually requires two columns. One column which is a date column and another column which is the data. Right? I mean they could do it different ways, but they didn't care. So we need two columns. Alright, so one is the date, and then the other is the, and then it should be a data frame. Alright, so they are, well, it doesn't matter, I mean, that's sort of what we have. So now the date column should be called DS. So that's a must. And if you look at also the, and we can take the package and change it such that it doesn't do this, we do care, so let it be as it is. So then I'm actually making a data frame such that it is in line with the requirements of this. And then the data column should be called Y. Alright, so and then it is. So that's sort of we prepare the data for this package. We need two columns, right? An ES and a Y. Alright, so that's the EF which we need. Alright. So now, well, the only thing we need to do is the following. Let's say we define a model of profit. Right? And then here we call the profit as a function. And it will generate a model by itself. I mean, we don't need to, I mean, here that's a very simple implementation of this profit that I'm doing with you. You can read the GitHub page and there are a lot of the stuff. But I will just stay with the simplest because I'm not going to tell you the theory. I think it doesn't make sense. But I tell you the details of how this pattern works without knowing the theory. So I will stay with the simplest form. And then it said we define a model like that. And that's it. So it means that we will rely on this package in understanding where the rates are, how the sort of cycles look like, and so on and so forth. Right? So we don't actually need to do much. And then here we say, all right, so fit it, fit this model to sort of this data, fit EF. Okay. So let's do the fit. So then we have the model. So the process is started and 1 second later it was finished. But those are for us. Well, now let's start using it. So now that it's fit, and we don't know what is it, but we can use it to forecast. Okay. So here that we need essentially some container where it sort of goes and calculates, sort of finds the forecast values and then puts them in there. Right? And then for that, then we need, well, let's put it, just follow what is on the GitHub page. Let's define futures. that's our profit model. So these are future values. So that's simply a container where, well, let's simply date. Alright? And then here we would say that make future data frame. Alright? And then it asks us how many periods do we want to do forecast. So that's the periods. And then we say 12. So that's 12 months. And we afterwards to define what is the frequency. Alright, so here we have M. So we have monthly data. And then if you have daily or yearly, then you say daily. And it will generate essentially future values for us. And that's the future wording. It says that this is ME, monthly estimation, so it doesn't matter. So let's look at the future. And that is this. Now that's simply dates, which we start from the beginning of our sample. And they're monthly, right? So they're, so that's sort of what we have, right? So it goes to end of the month, which is okay. Right? So we have them at beginning of the month, but it goes end of the month. So which is the beginning of the next month, but with one big difference, doesn't matter. So these are sort of what this future data frame looks like. So what we do. So as I said, that's simply a container that we can use it for forecasting. Alright. So let's now do forecasting with this model. Let's go to forecast model, so the values. Then here we would say the profit model that we have. Alright. Now predict. That's a function on the future. Now we have the forecast values. Now, alright, so let me just wait. I have to tell you what is this.
Forecast. So that was, let me just do that.
And that's open source, of course. We can always like look at the well, it says D or M. I don't know why. That's a future order, so probably we want to change it. Yeah, whatever. So that is what we have here. Alright, so I have the forecast values for this data frame on the model which we have defined and fitted. Alright, so let's fit it and we go. Now I just want to tell you what is in this forecast. What is it that it's sort of returns. So let's look at it. So these are the dates. Alright. It gets us the Alright. So the trend in the data is, so you remember, first it was constant, and then it was going up, coming down, and then going up again. Which is sort of stay constant. That is what is in this trend. Alright. So the trend, because that's an estimation, then it also provides us with the confidence level. I mean, the confidence bands are very tight. So it's sort of real level here. Because the trend is not random, essentially. This. And then there are y-hat, upper and lower. So these are the 95% confidence band on the forecast values. These two. And well, these sort of these additive terms and so on and so forth. Maybe I can leave for the moment out. Alright. And then there is something which is called yearly. Alright. So yearly is the cycle. Okay. So that's only the cycle, you remember, so we have a cycle, season, going up and down. So that is in the yearly. And then the last column, which is by half, is indeed the actual forecast values. Right? So till the end of the sample, which was around 603, there are in sample. Right? And afterwards, then we have the forecast values. So from here on, then we have the forecast. So things go up a little bit, then go down. Right? So that sort of gets the cycle. Right? So that's sort of what we have. Good. This is what we have in this data frame. Let's plot them and see. Okay. Let's plot and then see how they really look like. So this forecast I will just leave as is. Right? But for the purpose of plotting, then I will define a new data frame. I call it FTAS, which comes from the forecast. And then I set the index, so the time index for it. Right? So to be the forecast DS. Okay. That's a new data frame. Okay, well, I just said I could work with the original, but I want to leave the original as is. Because one can do a lot more with that, so we leave it as is. So that's the forecast, so that's the FCAS. Alright. So well, let's start sort of plotting the data. Alright. So if you remember, so in the previous one when I was plotting the forecast and I was looking at the last bit of the data, not everything, but rather in the very last, so that we see how the forecast looks like. So here I will do the same. That's actually not so long, and then we will be done with that. Let's do it this way. So let's have a start date for the forecasts, right? And that will be the end of the summer. That was for data, right? Or what was it called? No, DF, I called it. So that's DF dot, say, index. You look at the end of it. So that will be the starting date for forecasts. This is such that I have the confidence bands only for the forecast, not for everybody else. So that's sort of a point that I needed. And then I need an end date. An end date is sort of from the end, so which is the start date. Alright. And then we go essentially 12 months ahead because we do forecasting for 12 months. So I just want to have the end date. So we go to PD. There is a date offset function. Right? And I say that sort of offset the time by 12 months. Right? So that will be the end date. This is the start, this is the end. Right? So that's sort of where I leave the forecast. Right? So for 12 months. Alright, so, well, let's define a mask, right, as a combination of two tuples. So here I have the FCAST. So when the index is bigger than or equal to the start date F, and the FCAST index smaller and equal to n date. Alright, so that is what you as a mask, which you can later use it for my calculations and so on. So this is, as I said, for the confidence factor. If you don't do that, then the plots will be very ugly. You will not see them, right? You will not see what you have. Let's just start with plotting. So I'm going to start plotting the data. hard axis. Right, so that is what I have as an axis. And now let's just start with plotting the forecast. So here we take a plot. That is the f-task. Right, dot index. And then here we have the f-task dot count. So this is the forecast values. And let's also give this a label, and that is the forecast. So this is what we have. So now I want to also get the confidence bands. So remember we had the y-hat lower, y-hat upper, and the confidence bands that we also have in this graph, so it is so nice. So that's I will do it as an area, the forecast of area. I will say, well, give me the field between, right? On the f-cast, dot index, alright, but not everywhere. F-cast dot index, so that's already x. On the mask. Clear? So that's the, well, I want to do the confidence bands. The confidence bands I will do only for the time period where I did the forecast. That's why I define this mask. Because this mask is a true force. Remove masks. You can access sort of data. Yes. And now because that's a field in between, then we need two regions, upper and lower, so you can fill in between. Right. So here then we would say, alright, so I have the f-cast. So what was it? So we have a y-hat lower, right, also on the mask. We don't need it everywhere. And then the other part, which is upper. On the mask. Alright. Let's beautify it a little. That's the beautification. Let it be blue. And let's fix the alpha to 43. And then add a label, which is the confidence interval. Right? You know alpha, right? That's sort of the opacity. It could be 0 or to 1, and if it is 0.3, then it will be 1. Opacity is no longer about the factors. Now we can set bounds. Set the x bound as we have had before. Alright. And that will be well dt dot date, and we are going to solve it. Let's say 2022 to 1. Alright, so that's the beginning. Up to dt dot date. Well, that is say 2026. And the data was end of April plus 12, then will be the next year. Let's put it at 6. So that will be not a problem. And now we have a PLT dot width. A PLT dot legend. And a PLT dot
Part of this class is that we repeat and repeat programming in Python. We do it over and over again. The same thing. Right? Good.
Alright, let's look at this. Alright, so that's the profit. You see, I didn't choose any model, I didn't do any selection, so it does. It does what we did in the class. It does a bit more too, alright, but that's sort of what we have behind. Alright, so behind this model, behind this forecast of what we did. Actually, with our model, the previous one, we pretty much got the same, right? So we got the peak, the continuous value was good, and so on and so forth, right? So it was not actually very good. Actually, it was okay. That's why people like AR models, because they're so good. Right? So, and profit is also an R one, so that's not an actually different thing. I mean, the only nice thing about the it is that we don't do things on our own. So this is the profit, and this is the one that we have had previously. So the continuous manager are smaller, right? So because it takes care of the breaks. Alright, so maybe if you take care of the breaks and the cycle, then you wouldn't need so many variables to it. So then, well, that's sort of a decomposition because you have the cycle, you have the trend, you have the cycle component, and the AR part. So that's sort of what we have. But I also told you that this actually produces a bit more stuff. Alright? So let's maybe see, well, I mean, so here we have the trend and then we have the yearly. So we can go find them and then plot them. So what we can do is, we can, well, let's generate some figure, let's go with 2, and that will be from the, what do we call the model? Profit model. Model profit. Model profit. Well, I mean, this by itself can produce some very simple graphs too. And what is the plot component? Right? So that's a function. Plot components. Actually, from the forecasts, so uncertainty is true. You do the caption. When you start fixed sizes, so that's sort of very simple, right? So not going to be options. That the plot itself sort of produces some good enough plots. But we can do them on our own, but let it be as it is. Right? So we have the plot components of the forecasts. Right? So that's why I didn't want to change the structure of this so we can pass it to some of its own functions. Right? And then let's look at it. And that is what we get. Alright. But I mean, that's sort of a long-term, smooth sort of trend. Alright. And that's the break. The trend of the first one. The first one is immediately. Remember, so sort of a little bit things were going up. And then strongly going up. And then going too much up. Right? So that's the so this package actually understands these breakpoints and then fits lines. Now let's look at the data just so that we remember it, how it looks like. So that's the data. It was constant, going up, and then down, and then and so on and so forth. So that is what we had previously. Looks like that. So that's the trend decision. And that's a long-term trend. There's a linear trend, right? And well, this sort of is the pressure, so that's sort of linear. It's a little bit different, right? But that is the one which I would like to see. Right? Going up, down, and so on. So more or less gets what is going on. Do you have questions? much as we understood how to sort of in these last few days. I was with you Monday, Tuesday, Wednesday, today's which? Thursday. So the last few days, then I told you what is non-parametrics, and we looked at a little bit of the asymptotics, a little bit sort of. So what is the bias? What is the variance? We understood the bias variance trade-off, which is an important concept. Bias goes up, variance comes down, and vice versa. We sort of, so that was a bit of theory. We did some implementations of these non-parametric estimators, right? I told you how to estimate the density function, kernel density function, estimated with learned them. The slides that we have actually on non-parametrics are more than what I told you in class. Specifically, there is some more material on the uncertainty or the confidence bands or the normality essentially, central material for the current density estimators, right? Which are not part of your exam, I will not ask, but they are there for you. If you want, you can read them for yourself with the support, sort of the book itself, the book of so that's sort of what we came here, played a little bit around with the data, so forecasting, how do they work, how you can implement them in Python, and then in the end I also gave you something which you can use it. It's reliable, it's okay. It's not the best model. If you understand how it works, then you can make it better. So this is something which is, so how the cycles are estimated. So maybe one can do better. Or maybe you should. Not that you come up with a new model, but all the packages that they have, you come with them. First you have to understand. So how do they actually estimate this structure? And so on and so forth. So with that, I'm sort of feeling comfortable to leave it. Now, for yourself as an exercise, download the GDP of Vietnam for yourself and forecast. The weather forecast for the growth of GDP, the GDP growth. And then check whether your forecast, whatever you want to do, using profit or normal or anything, match those that central bank publishes. Suppose central bank does forecast. There was somewhere. There should be somewhere where you have forecast Vietnam. So you can do that, download it, and then play around. Okay. So that is what we have so far. So with this, then I can start with the new section, or the first section, which is what it is. Okay. If you have questions, you ask. But first, you work this through, and then you sort of you can go on to something. And that's what it is. I mean, the stuff that I have here are very much applied. Okay. So I'm not actually going to tell you how to estimate the large numbers when we come to large. And my goal is to tell you how to do the estimation and how to make sense of these estimators. Right? But at the same time, like I did with the time series stuff and the statistics, and I sort of reminded you, okay, so what is size, what is power, and we did some simulations here and there, and we'll do them too. Right? Because I think that the theory is nice, and also what you have had it before with some other courses. But once you come and then deal with the data, then you will have some other challenges. You're in 10 minutes thinking of how to model these guys. So how do you estimate them? What are they? And so on and so forth. So that's sort of, there are simple challenges that you have here and there. And then sort of once you start getting your hand dirty, then you will also be ready for your thesis. Your thesis will be soon, and then you have to do a lot of data work or so, right? Maybe theory, I don't know. So that is we did the same thing here. Alright. Good. I mean, these the slides that I have here are based on the book by Chris Brooks. Alright. That is the book. I mean, then, oh, I have the book with me. Maybe I should have. Oh, there is a PDF. But that's an older version. Edition. And that's the book. Right? So, what it says is introductory econometrics for finance, which is really introductory. It means that the first chapters are really reviewing of what is a function, and then what is OLS, and so on and so forth. So that's actually very simple. The reason I used it was not because of its simplicity. The reason I used it is that this guy has done a lot of interesting applied papers in his lifetime. He's a still alive, and he produces papers for preschoolers. Right? And that is the reason I chose this book for this class. It's not about the techniques, right? Like how I read it. But there are a lot of examples and sort of review of his own papers, or your main papers, and then summarize them and then make them up with a little bit of explanation about it. That's why I have this book. So, these are based on that chapter. Well, I mean, what we actually want to do is to understand volatility, how to model it. Of course, we know a little bit of modeling for sort of volatility, but I mean, well, let's just start with this picture. So these are the returns of the S&P 500. What do you see? They're always around zero, right? So the mean is zero, it seems like. But across all of this time period. So that's number one. Great. So you are actually focusing on the mean. Right? So they don't go up, they don't come down. It doesn't look like that they have too much sort of persistence in them, because if they did, they would have gone up for some time till the hammer comes, then goes down, and so on and so forth. Right? But it's not the case, right? So that's what the word is. So an average is you actually pay nothing. It doesn't make sense to buy this. We would buy something else. We would buy an ETF. Sure, something. What else do you see? At times where the variability or sort of the movements away from zero or away from the mean, if the mean is zero, are very strong. Right? And how to use them? Right? So we should call it volatility clustering. So here there is a lot of variation, then a little bit quiet, another big variation and stuff. We would have been nice if I had this out of and then quiet. Maybe have another patch where the volatility is high, there is big problems, there is the COVID outbreak, and things are quiet, then you have Trump showing up. There are essentially some stories to tell about clusters. So there are some reasons then. And if you see, these reasons are not so simple. So exposed, we know them. Right? Exposed, we know how this actually went down because of people who stayed home, didn't do anything. So markets went down. And then went up. So there was people didn't know what to do. Right? I remember I was teaching this class at this when this started in Eastern. And that was because there is a Turkish German university too. We're not the only one in the world. There are others. And when people didn't know, should we stay home, should we fly, should we not fly, somehow. We didn't know. And then the markets also didn't know what to do. So are going up and down. So you have a lot of negative and positive. So that's the volatility cluster. And because the reasons that we have behind these are not so simple, it means that these clusters form in a very non-parametric way. They are not simple. So maybe one can use parametric models, simple parametric models, to understand. And as such, then one either uses a non-parametric stuff to understand the behavior, or turns to classical means, which we know them from long term ago, namely the autoregressive traditional heteroscedasticity. That's what we know from the previous class. So very nice. So what we do is, maybe let's just give you a little bit of an idea of what we deal with. I mean, here we have the series yt, and then there are function or known function of today's shock and the past shocks. But that may be a little bit hard to estimate, because you have many shocks. Shocks are not one, two. So we can estimate this F non-parametric. Remember the first dimension because we had essentially with one variable it was okay. With two, where the dimension was h squared, so three was a cube, and so on and so forth. It was basically shrinking to zero very fast. It was not very easy to do that. So we need to sort of play a little bit around with that function, simplify a little bit, so we can sort of do that. What one does is that one says, okay, let this function have this specification. Right? And this specification actually has a mean, which is a function of the past. So it doesn't have t, that's very important. Right? And then we have this k, which is the variance, which is also a function of the past, times the current shock. Right? So the mean function and the variance function are only a function of the past. They can be a function of today. So that's sort of what we have here. And the reason we do that is that somehow we give it a bit of a dynamic. Today is a function of the past. Specifically the mean and the variance are a function of the past. If I have that function, whatever they are, then I will be able to forecast. Like we were doing with the R1. Today's value is a function of the past. And that is what we do here. Sort. And this is actually a function of the past. We have to become a little bit more careful with these, but sort of the functional forms that we have. The first simplification we do is that we say we have an additive term, there is a scale which looks like so, and there is a mean function, which is here. And both of them are non-linear, intrinsically non-linear, because of the way the clustering actually was happening, and as you mentioned, and then sort of the stories that we have. Alright. But generally we call this the non-linear mean, and then this is the non-linear variance that we have for this here. So these are the two warm-ups.
Related to the specific function,
Right.
do you have another form of this popular form?
You mean that the division that we have here, you mean that so you mean that this f, we do not do like that, we do not break it into this. So because this is a simplification of that. Now we need another simplification. Is it right? Is it right? Sorry, I didn't understand the question. So I'm trying to get this. So you mean that the additive term, additive model that I have here, you want some other thing. I do. This is actually very general advice. I mean, I don't know, because in statistics, then essentially we always have a location and a scale, which for all of the variables that you have around you. For example, normally distributed random variables, you have a mean mu, that's the location, and then you have a scale which is sigma. Right? So this scale and location parameters are indeed something which have a long history in the statistics.
We will use OMS and LL estimators.
To estimate them, yeah. Once you have a parametric model, then you can use the LL, you mean what? You mean maximum likelihood. This is what I mean, maximum likelihood, not local linear, but maximum likelihood model. Exactly. So we basically use afterwards, once you parameterize this, and we use an ML. You can use it.
So that's the most popular one in answering.
Yes. We have the location and the scale model like this. It's actually very popular. And the reason is that it has a long history in the statistics. History means 150 years. People like this location and the scale models. And then you still use it. Your question is actually very interesting. Can we do it different? I never thought of it because there's so much like this. Because if you look at, okay, so we are actually very advanced. I will jump now over the slides. So because you know them. So here, U that comes out, then it makes very easy sense to look at conditional mean of Y. Right? Because conditional mean, it's an expected value of U given the past is 0. So given the past, then this is a constant. So given the past, this will go off and the mean will go. So it becomes a conditional mean. That's why we have this. And the conditional variance will also be this. Because conditional on the past, then this will have will be the mean, so it will be non-random. And then when let's say we normalize the scale of this to 1 so that this becomes the conditional variance. Right? So these are actually stuff which are very much, as you said, they are very popular because they have meanings, conditional variance and conditional mean. They have a long history, as you said. So if we can do it differently, I'll laugh. Never thought. Very nice. All right, maybe let me continue. So here, if I have nonlinear mean and nonlinear variance, all right, then what? So, well, of course, you can linearize, right? So sort of this G and sigma will linearize, and then we go on. That's good. Sigma, that's sort of people like. Or you use nonlinears, nonlinear models. Right? Nonlinear models, of course, you know arch and large. You may use switching models, that is the next section. Then there is bilinear models, which are in non-code. Right? So there are sort of some ways of classical again non-linearities, so that we can actually take care of. Yeah. You remember Ramsey reset? So you can test for nonlinearities. But also one sort of popular way of looking at these functional forms or volatility by itself is to turn to machine learning. So that's another imprint, sort of fingerprint of machine learning. For example, one uses oftentimes neural networks or artificial neural networks when it comes to modeling, say, the nonlinearities that you have for the mean and the variance. I don't have actually the slides on this, so I wasn't supposed to talk too much about that. Maybe I can give you some simple implementation in the next days. You have to really think and then do some nice examples. I will look at that. These are artificial intelligence, sort of artificial neural networks are good. They have their own problems, right? But then at times they could be useful. Sort of, well, they're nonlinear functions, essentially. Right? I will tell you how to implement a neural network. It will not be in the exam, but for you to know. So to estimate a surface or a function of whatever form. Very simple implementation. But oftentimes one tell them black box because they are so big and so many parameters they have, and you don't know what is that, what does it do actually, you don't understand. It's actually very hard. So there has been a big literature recently, or sort of developing to make neural networks explainable. Alright. Oftentimes it's called AIX. The X is standing for explainability. Because well, when you have say this G function as a function of say T minus 1 and so on and so forth, oftentimes one wants to know what is the effect of this U on G. Actually T minus 1 is important, the shock of yesterday, or not. If the derivative of this with respect to T minus 1 is 0, then it's not important. But once you have G, right, then you can do such calculations. The neural networks do not give you G, and they give you, but they're so large that you cannot actually manipulate it. Deal with it directly. So they have their own problems. But let me just go over those and not talk more. But then we have the models of volatility, which we have here. So we have arch and gauge. Alright, so let's just start with looking at one of them. And one of these models. So this is a simple regression. We have heterosplasticity. And let's look at arch. So as I said, so that the scale variable, so that was called the one we had the G, and the other one, the sigma, is indeed the conditional variance. That is something you know. And the conditional variance is the expected value of u minus the mean to the power of u given the past. Oftentimes you assume this u to have a zero mean. So the variance will be simply the variance of u or the second number. So that's sort of what you know. As sort of stuff. But now, so let's look at this regression. Well, that's a conditional expected value, which sort of should remind you of simple regressions, right? In this sense that, well, if you have y equals a plus b x plus u, and then when we were using expected value of u and x being 0, that is what we have, then it would have meant that, so that is what we have. So it would have meant that the expected value of y, u and x is indeed a plus b x. Right? That's sort of what we had before. That's also a condition of expected value. Right? So think of this as y. These are the x's. Right? And that would mean that I could use maybe the same approach to model this expected value. That becomes parametric. So it becomes a parametric model if I turn to what we know from simple regression. And that is sort of the first sort of model. Right? So if I have sigma squared of t, which is given the past, we never write this. You remember that this is not unconditional. Variance but the condition, so condition of the past. Which is the expected value of ut squared given the past. And the simplest model that we know for that is to say that this is alpha 0 plus alpha 1 ut minus 1 squared, right? That is arch, remember? So if I want sort of to look at this model, well, of course you can add more lags. Right? So this is lag 1. So that becomes an arch 1. I could add more, lag 2, 3, and so on and so forth, right? Or Q in general. Ut minus Q squared, then it becomes an arch. That is what we do. Well, these are just again reviews, new stuff, because you have seen them before. But oftentimes one reformulates an arch model for the residuals, like so. The one says ut. So now I'm going in the direction of becoming parametric. So that's a parametric model. So we parameterize there, and we also sort of do a little bit more here. So here we say that ut is random shock times distributed with some distribution. But classes are ones that you assume that is normal, with zero. So it means that the shocks are assumed to be conditionally normally distributed. Conditionally normally distributed shocks with the variance which is sigma t squared. Well, these are stuff that you want to know. Do you remember the kurtosis of RH1? You know what is kurtosis, right? Good. You don't know. So what is the kurtosis of normally distributed random variables with mean and sigma squared? Very good. That is three. Right, so that is what we have. So, well, maybe just to pay a little bit attention to the art model, or sort of this conditional isolationism. So we will now go into a little bit of the data work. Let's say we download or sort of we use the data that we have and look at the kurtosis of S&P 500 returns. Right? Then you will get values which are very big, much bigger than 3. Right? Because generally you have 5 things that are the same, right? So you need in the financial returns. 5 days means essentially in terms of numbers that the kurtosis is larger than 3. Yeah? Well, we can go beyond the kurtosis of RH1 if you haven't done before. And then you will see that it will be a function of alpha 1. And it will be in such a way that this kurtosis is bigger than 3, which is larger than 3. And by itself, I mean, sort of, now it's actually magical. Errors are normally distributed conditioning. But because of this conditioning, they are in such a way that you will have a kurtosis which is larger than 3, which makes this combination appropriate for financial series. Because financial series generally have a kurtosis which is bigger than 3. And that is nice about these models. So one of the interesting features of this conditional elasticity models is that they have kurtosis which is larger than 3. And large kurtosis is an important characteristic of most of financial returns. All of them have large kurtosis. All of them have 5 things. So, well, if you are not too technical, then you can work with mean and standard deviation, skewness and kurtosis, then you will be liking this model. Right? Because it has a feature which is matching or could match the behavior of financial series. Larger kurtosis is possible to take care of with these models. Right? That's important. Let's have a break, please. These discussions that I'm doing with you are very simple. Right? They're reviewing stuff like this and also highlighting the importance of these models. That is what I want to do. And then we use them. We can do program. Oh, this is funny. Not giving